Welcome to the Electrogravitic Experimental Results. This is the sixth video of the Electrogravitic Experiment, which is the third experiment in the New Electromagnetism version 5 experimental supplement. And New Electromagnetism version 5 is the fourth book of Ethereal Mechanics. That's why this has a long code, Ethereal Mechanics Book 4, Experiment 3, Video 6. This is being released to Patreon members on the 4th of August, 2024. It will be a YouTube premiere 5 September 2024. Okay, this is a photograph of the experiment in operation. This is the thermal imaging camera of this exact same, this comes from the same FLIR camera. So what we have here, for those people that are unfamiliar with this experiment, we have current running around a square loop, hundreds of amps, and at the corner of the loop where the current has to take a right-hand change of direction, charges are accelerating, which creates an inertial effect that can be picked up to a coil that is placed right near the junction. Okay, and we're running this two ways. The first one is a 30 gauge copper wire. We're trying to run that with 100 amps, but our op amp in here was howling, so I decided to drive the power transistor directly from the pulse generator, and that limited us to get about 75 amps through the 30 gauge wire. This is the thermal image, and you can see the hottest part is 128 degrees. It's not really hot to the touch. It's because we're at 0.1% duty. It has plenty of time to cool, but you know, the thermal imaging camera makes it look like it's like molten lava in the little channel. Okay, the pickup coil is 100 turns of 30 gauge wire, and that's tied into a times 100 amplifier. We're going to show you the full video. You get to see this outside of this picture. The other experiment that we ran it after we filmed the little video, is we used 14 gauge nichrome wire. So in this video, we're going to demonstrate the experiment. And again, the two experiments, there's one with 30 gauge copper wire, another one with 14 gauge copper wire. And we're able to get that one up to 60 amps. And let's just say it outright. We obtained strange results. My friends, this is a rabbit hole for the ages. This snippet was filmed while taking the data for the 30 gauge copper experiment. And the effect in that was so small that I thought the experiment was null. It wasn't until I started doing the nichrome experiment after I took the video that I realized the effect actually is there, and then was able to zoom in on it, and we'll show you the results. And when we look back at the copper results, they're there. We just have to zoom in to express those results. So again, when I'm filming this little snippet you're about to see, I'm basically talking in terms of this was a null result. And even if it were a null result, that would be okay, because I told my Patreon members a while back that a null result would actually be more interesting. This is a nearly null result, but we also have other anomalies. So we got a lot of good stuff out of this experiment. And we're going to be improving the experiment to pull this effect out. We'll talk about that more in a minute. Let's go to this video. This is the full power results of the Electrogravitic Experiment. Let me show you the scope. Okay, these are the scope pulses of the experiment. Let me explain what they mean. The red line is the input pulse coming from our pulse generator. Right now, the pulse generator is set up to have a 0.5 millisecond rise time, a 1 millisecond duration, and then a 0.5 millisecond fall time. We did the slow rise and fall times to keep these little yellow pulses tame. Okay, the blue trace is the current in the circuit. Okay, each box going up is 20 amps. So we're at 2, 4, 6, almost 75 amps. Okay, and the reason why we can't go any higher is because we are at the limit of our voltage. The maximum voltage that we can put out on this pulse generator is 10 volts because we're driving the transistor directly. In the original design, we had an op amp driving the transistor, which would have been able to drive it to a higher voltage, but the op amp was howling because we had too much distance between the op amp and the controlling transistor. Here we have basically an open loop control, so there is no possibility of this howling. And in fact, we're actually getting a nice signal. The current is not doing too bad as far as following the pulse. This little downwards ramp here is caused by the fact that the wire is heating up and the resistance is going up, which is dropping the current in the emitter. But it's not too bad. And that's one of the reasons why I reduced this pulse from 10 milliamps. I've reduced the pulse width from 10 milliseconds to about 2 milliseconds, is to reduce this droop in the pulse caused by the wire heating up. And it's actually pretty stable for 1 millisecond, which is good because we're in less probability of burning up the wire. And because we have a much shorter pulse width, I've only really have connected 2 of the 4 capacitors to keep the voltage across the transistor reasonably constant. Okay, let's get back to the last trace. The gold trace is the voltage measured at our pickup coil, this little square coil here that is perpendicular to the emitter coil here. The emitter coil is a single strand of 30 gauge copper. The pickup coil is 100 turns of 30 gauge wire, and that's going into our times 100 amplifier, the newly designed one, and that's giving us a nice clean result, which is halfway decent. Now, these downward pulses you see here and the upward pulse you see here, those are due to the inductive coupling the source wire to the pickup wire. And because we have inductive coupling, it means that our pickup coil is not perfectly aligned. Let me show you what I mean. Okay, I'm going to put slight, and I wish I had 2 cameras so I can show you what I'm doing and show you the pulse trace at the same time. But I'm going to put a slight amount of force in this direction first. I'm going to twist this guy just like this. I'm just going to apply a little bit of force just like that, hardly move it, and twist it this way. Okay, now when I do that, you're going to see those fangs are going to get worse. They're going to get bigger. Okay, so that means that this guy here is cockeyed a little bit this way. So now what I'm going to do is I'm going to put the force in the opposite direction and twist it a little bit this way, which will align it better and it will cancel those forces. Now let me show you that. So now I'm going to apply a little bit of force and you can see they pretty much go away. Okay, that was the intent, but the 3D printing actually wasn't bad because we're only off a slight tiny bit. Okay, so now, I'm going to leave those fangs there because those fangs aren't really bothering us too much. In the middle here, in this little section of the coil, that's where we should see the effect. And we don't. The only thing we get is this little artifact over here, which I can't explain. We do have another artifact that's moving along, but I'm pretty sure that's not synchronous to our experiment. That is noise coming from somewhere else. But let me do this for a minute. Let me increase the sensitivity of the scope. Okay, and we can see that pulse there, this guy is a curious anomaly. He is synchronous to us because he doesn't move. He does get affected by the noise that rolls underneath him, but for the most part, he is solid with the experiment. Now, let me do something else. I'm going to change. I got to move my camera to the other hand. Hold on. I'm going to change the pulse width to 3 milliseconds. Okay, and that artifact is still there, and we don't see any other artifact. Okay, so I don't know what's causing this artifact here. This is very intriguing. Very intriguing. Again, another experiment where we got something that's unexpected. Okay, and the other thing that's going on is we're not seeing what we should be seeing. What we should be seeing is a pulse here in the yellow that corresponds to the current in the circuit, which means our electrogravitic pulse, as predicted by the software, is not there. Now, until we figure out what this is, we're going to assume that this is maybe it's not it, that this is something else. I don't know. I don't know what this guy is. Let me turn on the thermal imaging camera. Okay, you can see the heat on the coil. The coil is kind of blocked by the pickup coil, but you can see it's hot. I mean, it's not really that hot. Okay, it's 133 degrees Fahrenheit, which isn't bad. Now, the more important thing is that the corners should be hot according to other people, what they're saying. And it makes sense. The corners are not hotter. Why aren't the corners hotter? That little star should be tracking the hottest thing in the picture. And the only reason why it's going lower toward us is because that's a closer point. If I put it more evenly over the top of this, okay, it's bouncing between all parts of the wire, not necessarily the corners. The corners are hotter. This is not showing that they're any significantly hotter. Okay, and the amperage that we're putting through this, like I said, is about 75 amps. So we should have seen something if the effect were true according to the theory. Oh, and the other parts that are getting hot here are, that's the transistor, which is at a nice chilly, where's the temperature? Oh, there. 110 degrees Fahrenheit. A hot summer day. That's pretty cool. Okay, everything else is stable. Capacitors are stable. All right, so that is the demonstration of the electrogravitic experiment. Okay, so this is a screenshot of the copper. Let me explain again. I know I explained in the video. This is the output of the pulse generator, which is driving the base of a power FET directly. We can only go to 10 volts on this, so we couldn't get the power FET to produce enough power to the targets or the source wires in order to get the full 100 amps. Because according to the theory, the effect goes up by the square of the current. I'll say that again. The effect goes up by the square of the current. Okay, this is a measurement of the current through the source wire. And you can see for the copper, there's a slight downward trend in this. That's because the wire is heating up and the resistance is increasing, and therefore the current through the wire is decreasing slowly. This here, this is what we're calling a induction fang. The fangs result because the pickup coil is not perfectly aligned, and it is coupling some of the inductive effects of the source. And I kind of like it. It kind of shows us that those inductive effects are there, so no one can argue that the effects we're seeing are inductive effects, because the inductive effects only occur when the current's doing time changing. Time changing, that's when we see them. So when the current's rising up, we get the current, the voltage in the pickup is in one direction. When the current's decreasing, we get the pickup current coil shows the opposite direction. Okay, you will also notice that we have an anomaly in the middle. I have no idea what causes this anomaly. Some of the thoughts is that there may be a RFID tag in the room I'm running the experiment, which is getting excited by the really intense magnetic field, and it's chirping back. I don't know. But this is synchronous to the experiment. So it looks like it's an artifact of the experiment, because when I change the pulse width, that stays in the same place. Okay, so that is the anomaly, and then we're going to talk a little bit more about that in a moment. Now, the effect that we should see, if it were positive, should be a 50 millivolt rise above the flat line. An anti-gravitic result would be the opposite direction. As you can see here by looking at this data, it doesn't look like this thing even moves off the line. That's why when I did the video, that's what I was assuming. Okay, but let's go in and let me show you how to interpret what the scope is showing you. Okay, when the fangs are normal, when I mean normal, they're not affected by anything else. Okay, the fang tops should be flat, except for the places where the current's at very low, because in those low current ranges, the transistor is barely on, and there's a nonlinear effect there. So this is how the fangs should look if there's a completely zero effect. And the null result, the signal between the fangs, would be at the same level as the signal outside the fangs. Again, the fangs would be flat-topped. So a null result occurs if there is no effect, or the level of effect is too small, which I think worked out partially, or gravitic and anti-gravitic effects are both present. This gravitic and anti-gravitic effect is what new electromagnetism V3 said there should be. Okay, so any V3, the effects canceled. Let's just keep on going. So just because we have null result doesn't mean we're out of the woods yet, but let's just go on. For a positive result, the expected gravitic effect should look like a flattened version of the current pulse. Sloping sides, flat top, etc. And then when we add this to the fangs, this is what we're going to get. We're going to get a slight sloping of the fang tops, and we're going to get a slight displacement off of the zero line. Okay, but we can also get an anti-gravitic effect, which is basically everything going in the opposite direction. Because it's negative going, we have a little extension of this slope here. And also, when we're recovering, that's going to cause us to basically have a little slope on this guy. Also, this guy might end a little higher off the line before it recovers. We do, in fact, see that. Now, the slope here does depend on the relative amplitude of the fangs. So in most cases, we try to realign the copper pickup coil to minimize the fangs, which minimizes the inductive coupling. So if we take a closer look at the results, okay, here's the copper, 100 millivolts per division. Now you can see we have a slightly degrading slope on the current here. The current's very constant, so the temperature of the nichrome isn't affecting the resistance as much as the temperature of the copper is affecting the resistance. But here, we definitely see the slope of the fang, as would be expected for an anti-gravitic effect, and the opposite slope of the opposite fang, and we definitely have a displacement off the line. Now, it looks like we do have some kind of what do you call it, decay curve in there. That's exciting. That we don't know why curves. It should be a flat in there, but it's a decay curve. Don't know what's causing the decay curve. Still don't know what's causing this anomaly here. And over here, when we looked at it closely, look at that. The green line touches the bottom of the flat line. Okay, it's in line with the flat line, which means it's slightly anti-gravitic here. The slope kind of shows it's anti-gravitic over here. And the other side of the anomaly, it goes gravitic with the appropriate slope up here. That's very exciting. Looks like the anomaly has something to do with it. Almost like what we were saying before, that there's both gravitic and anti-gravitic effects and they're out of phase. That's very exciting. But that's just theory right now. We have to do a lot more work on this. This is going to be a major rabbit hole. Okay, but you can see that we're getting something a little smaller than I'd expected. But then again, I have been complaining all this time that I think the published values for the material properties are not valid. But that's another thing to be worked out another day. Okay, now, so what I did is I took the copper. We did take high resolution measurements down to 10 millivolts for the copper. We placed the green line on, and sure enough, the earlier part looks anti-gravitic. After the anomaly, it goes gravitic. And then I worried, well, maybe this is coupling into the effect. Maybe this slope, because this is a current change. And because our fangs are still there, maybe this is coupling into it. Maybe that's the reason why this side is a little higher. Because when the current goes down, that drives the coupling up. And that would correlate with that. But if that were true, then this side should be above the line too, because that's downward going. So there's a conflict here. So what I did in the next experiment is I realigned the coil to minimize the fangs. Because if I minimize the coupling of the fangs, then that also minimizes the coupling of this slope to this curve. And if you look really, really closely, we have an anti-gravitic effect almost all the way across. Okay, and it's there. I mean, it's 1 pixel, but it's there. And I think we got a blow up of this. Yeah. So what I need to do is next weekend, I'm going to go down and look at this in more detail. But minimizing the fang does, in fact, decouple this from this measurement here. Very, very, very interesting. So the experimental path forward, we got lots to do. Going to check all the math, all the simulations, the scope connections, everything to see if there was a sign error. Because it looks like we're getting mostly anti-gravitic effects. Okay, I was expecting gravitic effects. Okay, and reconcile lower than expected amplitude. Can it be reconciled as gravitic and anti-gravitic cancellation at the same time? And the reason why we see anti-gravitic is because the anti-gravitic is slightly more than the gravitic. That is very possible. Because the effect we should be seeing should be about 10 times bigger than what we're actually seeing. And so what it might be is that we got both effects. They're canceling each other, and there's just a little bit more anti-gravitic. And that's why we see a slight anti-gravitic effect. Again, we're going to revisit the NEV5 and recheck all that math to see if that same idea applies to us. And then if we can find a way then later to put the gravitic and anti-gravitic out of balance, maybe that involves much more resistive wire. I don't know. Okay, then we definitely have to understand the cause of the anomaly. This is of great importance because the anomaly is about the amplitude we're looking for, strangely enough. We need to get the op amp working now. We've got to put that back in so we can drive to higher currents and also keep the current constant. We don't want that current sloping while we're trying to take the gravitic measurement. And then we need to improve the pickup coil alignment to minimize the fangs and the inductive coupling. So we've got a lot of work ahead of us on this. But this is exciting because we've got a carrot now. So for the production path forward, this could throw a monkey wrench in. And so what I've decided to do is I'm going to post to the senior Patreon members, the bridge officers and the first officers, I'm going to put up a questionnaire how we want to proceed. There's option 1, stop all production and premieres. Just stop all video production and focus on this, reconcile this. Now, this could take months. I mean, the Patreon members would get their statuses every week of where we are, maybe every other week, depending how busy things are. And this actually may result in new electromagnetism, V6, depending on how disruptive it is to the existing NEV5. Okay, the second option is to place a caveat in the NEV5 paper saying we got some interesting results. The results of this section of the paper is on hold until we reconcile the experiment, but we're going to get the paper published with that caveat anyway, get it out to everybody. Just with a caveat saying we're not finished here, basically is what it's saying. And then finish up the NEV5 videos and papers and the cosmology video series. I have a potential release date on the last slide of when things will be released if we go this route. And then finish up the cosmology video series and be able to return to this experiment either by winter break 2024 or early 2025. Or option 3 is to do a 50-50 where we kind of do number 2 at half speed. We do a premiere every other week. And we work so we do odd weeks and even weeks kind of deal. That's another possibility. So even though this is being shown to Patreon members first, to those, it's going to be eventually published to the premiere to YouTube. You YouTube folks, everyone out there in the video, in the public world that's watching this, listen, I could get a lot more work done this faster if I didn't have a JOB to go to. But right now my JOB is the #1 funding for this venture. Your help would be greatly appreciated. $5 a month isn't going to kill you. Okay, come to my website. This is out of date. I don't have all the videos linked in here yet, but I will. I will catch this up someday. But the ethereal mechanics stuff is all up to date for the electrogravity stuff is up to date. So if you go in here, you'll find all the electrogravity stuff. New electromagnetism V5, I update the videos for that. Right now, if you want to find all the videos for this, you just got to go to this YouTube, to the YouTube channel and type in NEV5 and the tag for the video series will come up. Okay, this is the blog site. Big shout out to Sebastian. Again, if I could get my JOB out of my hair, I would be able to have a lot more time to spend here. But I shout out to Sebastian for doing this and taking care of it. Thank you very much. This is the YouTube site. You can get there by etherealmechanics.com. Usually, sometimes this works, sometimes it doesn't work. If not, just go to YouTube, search for Ethereal Mechanics, and look for the picture of Julie with the Ring of Fire. And then basically go to playlists. All of the videos will be in their own playlist, whether they're transvariants, electrogravity. We don't have any ethonic, pretonic ones yet. Vortex algebra, rules of acquisition when they're produced, cosmology when they're produced, and all the NEV5 videos should be. They're not going to be in order yet, so just go by the sequence number. This is the potential release date if option 2 is chosen. We're going to keep our every Thursday night for public releases, and these are the Patreon releases. These videos have already been released to Patreon. I think we released them last year before we got onto the Electrogravitic experimental build. And we'll begin reproducing the remaining videos for the NEV5 starting next weekend to get this out of the way. Okay, this assumes that we put the electrogravitic experiment on hold until we get all the production done. Anyway, thank you very much.